Hey everybody, so in this video we're going to talk about two different sections, 8.5 and 8.1, but both of these sections cover the topic of solving systems with two equations and two variables. This should be a review for you guys except for some new vocabulary. Okay, so we're going to go over the vocabulary first and then we'll use it in our examples and hopefully that will help you feel comfortable with it. Okay, so the first thing we're going to talk about is consistent and inconsistent. Okay, so if a system of equations has solutions, if it has one solution or if it has many solutions, we say that it's consistent. Okay, so the opposite of that Okay, so a system of equations is inconsistent if it doesn't have any solutions. Okay, so those two things are opposites. Either it has solutions, it's consistent, or there's no solutions, it's inconsistent. Okay, so the other ones that we're going to talk about are independent and dependent. Okay, so a system of equations is called dependent if you could have rewritten it with fewer equations. Okay, so for example, if you have a system of two equations and one is just a multiple of the other, that's something that would be called dependent. Okay, and this is going to give you infinite solutions. So if you've seen examples, you should have seen examples where you get infinite solutions. Those are all examples of dependent systems. So I'm going to give you an example. If you have this, and then you just had 2x plus 2y equals 6. Okay, this second equation isn't adding any additional information because it's really the same as this first equation, right? And so this is a perfect example of a dependent system, okay? And these dependent systems will have infinite solutions, okay? Now the opposite of that would be independent. Okay, so we say it's independent if it couldn't be written with fewer equations. Okay. And this is what you're used to seeing. So most systems of equations that you see and are trying to solve are going to be independent. Okay. Only this kind are going to be dependent. All right. So that's our new vocab. So let's look at some review examples about solving, and hopefully that will allow us to practice our new vocab. Okay. Okay, so in the first example, we're going to solve using a graph. Okay, so if we're going to solve using a graph, we need to just graph these two things. Okay, so here we go. Okay, and because I have this negative 12, I'm actually going to go by 2's. So this is going to be 2, 4, 6, negative 2, negative 4, negative 6, and then same here. 4, 6, 8, 10, and then 12. Okay, so this is negative 10. All right, so I'm going to graph the first one just using the intercept method. So if I plug in 0 for x, then I get 2 for y. So I'm going to plot the point 0, 2, which is right here. Sorry, I was pointing at 2, 0. And then if I plug in 0 for y, I would get x is 4, and that's going to be right here. Okay, and I'm going to connect those two with a line, like that. Okay, so this is my first equation. All right, now I'm going to graph the second one. Okay, so just to remind you how to graph these, you could also use the slope-intercept method. So my y-intercept comes from this, it's 0, negative 12, which is here. Okay, and then my slope is 3 over 1. Okay, and because I decided to go by 2's, I'm going to say that this is the same as 6 over 2. Okay, so 2, 4, 6. Okay, and then over 2, 2, 4, 6 over 2. Okay, and then I'm going to draw my line. Not very straight, but should be over here a little bit more. There we go. Okay, so now we want to think about where the solution is. Okay, so the solutions, all the solutions to the first equation are all of the points on this line. So if you picked any point off this line and plugged it in here, you would see that it checks, it is the solution. And then same thing here, if you took any point off this line and plugged it in here, you would find that it's a solution. So if we want something that's a solution to both, we want a point that's on this line and a point that's on this line. Okay, so it's going to be our point of intersection, which is 4, 0. Okay, so we're going to write our solution as an ordered pair, 4, 0. Okay, so that's the idea of solving by graphing. Okay, now to use our new vocab, there is a solution, so we would say this is consistent. Oops, I can't spell. Okay. Now, because there's not infinite solutions, we know that this is also independent. Okay, now for a two-dimensional system where you have these, like you're graphing two lines, independent will mean that the two lines are independent of one another. They don't look the same. Okay, so that's another way to know that this system is independent. All right, let's look at some other examples for graphing. Okay. All right. So here we go. We're going to graph these two. So this is my first one, this is my second one. Okay, so for the first one, I'm probably going to use the slope-intercept method just because it's in slope-intercept form. Okay, so my first point is going to be 0, negative 3. Okay, so 0, negative 3. Okay, and then my slope is 2. So I'm going to go up 2 and over 1. Okay. Just to remind you, you could also go down 2 and left 1. Okay, so this is going to be my first graph. All right. Okay, Then I'm going to look at my second one, and for me, if it's in standard form like this, it's easier to use intercepts. Okay, so if x is 0, y is -2. Okay, and if y is 0, x is 3. Okay. There we go. Okay. Now, this kind of highlights an inherent problem with this method is we can kind of guess where this point is, but it's hard to really tell where this point would be. Okay, so we think this point is somewhere between 0 and 1, right? Because it's not quite to this point that's at 1. Okay, so maybe we would say like 3/4 or 0.75. Okay, and then the y value is between -1 and -2, so like -1.5. Okay, so from looking at the graph, all we can tell is that it is approximately 0.75 and then -1.5. Okay, so if it says to use the graph, it's totally fine to estimate. Now there are other methods, so in general this might not be the best method because you would have to estimate, but for now, because it said solve by graphing, we are going to graph. Okay, let's look at a couple more examples of this. Oh, again, this has a solution, so we would say it's consistent. Okay, and there's not an infinite number of solutions, right? And the lines are two separate lines, so that would be independent. Okay. All right. All right, so we actually just graphed the line y equals 2x minus 3. Okay, so we'll graph that one first. We definitely know how to graph it. Okay, so we would go up 2 and over 1. Okay, so this is our second line. All right, then we want to graph the first one, which is 2x plus 1. So our y-intercept is going to be 0, 1. Okay, and then we're going to go up 2 and over 1. Okay. Okay. So remembering that our solution is the point of intersection, look at these lines. Is there a point of intersection? Well, no, there isn't. Okay. How can we be sure that they don't cross like really far apart? The slope of this line is 2. The slope of this line is 2. That means they're parallel. So we know for sure that these aren't going to cross, okay? Which means that we have no solution. Okay, so this is our answer, okay? And just to practice our vocab, no solution, again, means that this is an inconsistent system. Inconsistent, okay? But because the lines are independent of one another, right, they're separate from one another, it is still an independent system. Okay. All right, we'll do one more example of solve by graphing, and then we'll review the algebraic methods. Okay. We're going to use this line again. Okay. All right, so this is our first line, which we know how to graph because we've graphed it several times now. So we're going to start at -3. Okay. and then we're going to go up 2 and over 1. Okay, so here's our graph. All right. Now for this one, we're going to go ahead and use the x and y intercept method. Okay, so if x is 0, then y is going to be -3. So that's this point here. And if y is 0, then x is going to be 6/4, which is 3/2. So that'll be this point right here. Okay, so that means when we go to draw our second line, we're actually looking at the same line as the first line. Now you could see that if you put this into slope-intercept form, you'd see that it's exactly the same as this line. Okay, so this has infinite solutions, right? Because where's their point of intersection? Well, it's the whole line is a point of intersection. So there's infinite solutions, okay? And remember, that means that we have a dependent system. Okay, so this is like a textbook example of something that's dependent, okay? Because you only have one line. The two lines are not independent of one another. They're the same, okay? So that's what it means to be dependent graphically, okay? And whether or not it's consistent, well, there are solutions. There's a whole bunch, so it's still consistent, okay? So got our vocab in there. All right, so there's some examples of solving by graphing and what it would mean to be consistent and inconsistent, dependent and independent for those graphs. Okay, now let's do some solving algebraically. Okay, so solving algebraically just means solve without a graph. Okay, so for us, there's two different methods of solving. Okay, so for this one, we're going to use substitution. Okay, I'm going to assume that you guys know how to use substitution, so I'm not going to tell you how to do it. I'm just going to use an example to refresh your memory. Okay. Okay, so we're going to plug in this into our other equation. Okay, so we would have 2 times w, which is -2r plus 7, equals 14 minus 3r. Okay, so that's why it's called substitution. You're substituting this expression in for w. Okay. Okay. So here we go. We would subtract 14 from both sides. Okay, add 4r to both sides. Okay, and we would get r equals 0. Okay, and now we're going to plug this back in to this equation. Okay, so w equals minus 2r plus 7. Okay, which gives me w equals 7. Okay. Now, if you don't have x and y, you might be asking how you could put your answer in an ordered pair, okay? And you just do it alphabetically. So r first, w second. Okay. All right. So we can see that we do have a solution, which would mean that this is consistent. Okay. And we have a single solution, which means that this is independent. Okay. All right. Now let's move on to the other solving method. Okay. So this method is either called combinations, okay, or it's called elimination. And that depends on just who asks, okay. It doesn't matter what you call it, they both make sense. So it's either called combination or elimination. So if you've learned either one of these methods, they're the same. Okay, so let's do one example. Okay, so the point of this method is to multiply one or both of these by a constant so that you can eliminate one of the variables when you add, okay? So you have a choice here, okay? So you could either multiply this by -3 to get opposites, so when you add them you get 0, or you could multiply this by 2 so that this is opposites and when you add them you get 0. Okay, so let's multiply this by 2. So that would give me 2x plus 4y equals 8. Okay, and then I'm just going to copy my second equation. Okay, so now when I add these two together, 2x plus 3x is 5x, 4y plus -4y is 0, right? That's the point of this method. You want one of the variables to eliminate. Okay, 8 plus 2 is 10, and that lets us solve for x. Okay, now the biggest mistake I see with this method is that students will forget to use this to solve for y, so let's go ahead and do that. So we have x plus 2y is 4. Okay, and then we're going to write our final answer as an ordered pair, 2, 1. Okay, now because this has a solution, this would be consistent. Okay, and because there's only one solution, this would be called independent. Okay, all right, let's look at a couple more examples of that method. Okay, now either way, if we want to eliminate these, we kind of need to multiply the top one by -2. So let's do that. That would give me -12p minus 4q equals -2. Okay. So now when I add these two together, -12p plus 12p is 0, -4q plus 4q is also 0, and then -2 plus 2 is also 0. Okay? Now, it's important to note at this point that this is a true statement. Like, this is obviously true, right? 0 does equal 0. Okay? So just to remind you guys, this is when you get infinite solutions. Okay, you can see that the two equations are multiples of one another, right? They're really the same equation. Okay, and that's why you get infinite solutions. If you imagine the graph, you're graphing one line and then you graph the other line right on top of it. Okay, so this is also a case of something that's dependent. Okay, now because there are solutions, this is still consistent. Okay, it doesn't matter if there's one solution or lots of solutions. If there's solutions, it's independent. It's consistent. Okay, if there's one solution, it's independent. If there's lots of solutions, it's dependent. Okay, let's do another one of these. Okay, now when you have something like this, okay, you need to put both of them in standard form before you even get started. Okay. So here we're going to subtract 3b from both sides. Okay. All right. So now we're looking to eliminate. You can either eliminate u or v. It really doesn't matter. Okay, so maybe let's do, I don't know, let's do v. Okay, so I'm going to multiply this one times 3, and this one I'm just going to copy it. So that's give me 6u plus 3v equals 12. Okay, and here I'm going to get 3u minus, oh, I'm not multiplying this one by anything. U minus 3v equals 2. Okay, so now I'm going to add them together. U plus 6u plus u is 7u. Those cancel, and this is 14. So I get u equals 2. Okay, and then I'm going to use that to find v. So 2u plus v equals 4. So v is 0. Okay, and that would give me my final answer to 0. Remember, you're just listing them alphabetically, u and then v. Okay, so this would be consistent because there is a solution, and independent because there's only one solution. Okay. All right. Couple more examples of this. Okay, so these are actually already set up to eliminate, so you, oh, not quite. We're going to multiply one of them by -1. It doesn't matter which one. Okay, there we go. Okay, so then we're going to add them. -x plus x is 0. Y plus -y is 0. -5 plus 7 is 2. Okay, so in contrast to what we did in example B, this is a false statement. Okay, and when you get something false like this, that means there's going to be no solutions. Okay, because there's no solutions, that means it's inconsistent. Right? Remember, inconsistent just means there's no solutions. Okay, but because these two lines are different, right? They're different lines, this is going to still be independent. Okay. All right. One last example of this. Okay, so in this example, you can see that we're going to have to multiply both of them by something, right? You can't pick an integer that when you multiply 2 by that integer, you get 3. Same here. You can't multiply 3 by anything to get 5. Okay, so if we're trying to eliminate x, we might multiply this by 3 and this by 2, because then we'll have 6 and -6. Okay, so that would give us 6x minus 9y equals 9. And here we would get -6x, right, which is what we wanted, plus 10y equals -12. Okay. So when you add these two together, 6x plus -6x is 0, -9 plus 10 is 1y, 9 plus -12 is -3. Okay, and then we're going to use that information to find the value of x. So 2x minus 3 times -3 equals 3. Okay, you can plug it into either one of the starting equations. I just usually choose the first one unless the second one is much simpler. Okay. All right, so I get that x is also -3. So my ordered pair would be -3, -3. Okay, now since there is a solution, we would say this is consistent. Okay, and because there's only one solution, we would say it's independent. Okay, all right. I hope this refreshed your guys' memory about solving systems of two equations with two variables. It's important that you really understand the combination or elimination method as we move on to the next section. So if you have any questions, let me know, and I'll see you guys soon.